Sit on a frictionless rotating chair and push against it to initiate your rotation. Once your feet are off the ground, you'll notice that your rotational speed remains relatively constant. Now, extend your arms outward, effectively increasing your size while keeping your mass constant. As a result, you'll observe a decrease in your rotational speed, which will eventually reach a new constant value as long as your arms remain extended. Next, bring your arms back close to your body, and you'll be surprised to see that your rotational speed increases, eventually reaching its original value. Its explanation lies in the law of conservation of angular momentum. Let's compare these two scenarios side by side. Since there was no external torque acting on the system consisting of the man and the chair, the total angular momentum must remain constant, whether before or after the arms were extended. Angular momentum is the product of angular speed and the moment of inertia. The moment of inertia is proportional not only to the mass of the object but also to the effective size of the object. On the left, the moment of inertia is smaller, which is why the rotational speed is higher. On the right, the moment of inertia has increased, leading to a decrease in rotational speed. In both cases, the total angular momentum of the system remains the same and constant.